we talk about discrete random variables, their mean and their expected value. What does that mean? Well, discrete means that we have specific numbers that we could sort pieces into. So for example, if we were to talk about the number of children per family, people might have 0 kids in the family. They might have 1. They might have 2, 3, 4. We'll go 5 plus. Okay? And you could sort people accordingly. Big John, what do you got in your family? Number of children? 2. Theo, what do you got? 2. Greta?
4.
Lily?
3.
Kira?
3.
Hannah?
3.
Bella?
Why would there be a 0?
Yeah, so, well...
Do you count yourself?
Well, my point, in here, nobody would be a 0, right? Right, but if we were to talk to a family unit, right, you might have a husband and wife that don't have kids yet, right? Something like that. So you can see, everybody see how you can be sorted, and the fact that we have very specific numbers, these are discrete. Look at the difference here, whereas we talk about, say, height of women, okay? If I ask Kira her height, Kira, do you know how tall you are? 5'9", so that'll be 69 inches. Okay? And we can put that there. Hannah, how tall are you?
5'5".
5'5", so we'd be 65 inches. Okay? Liv?
5'2".
5'2", maybe 5'2 and a half. Maybe 5'2 and 3/4.
It is 5'2", 3.
5'2 and 3/4. Maybe 5'2 and 5/8, right? Is it true that we could put Liv, instead of being at 62 or 63, that she is somewhere in between those? You get my point? And so height ends up being a curve like that where you can achieve any value within that range. Okay? So if you're looking from a mathematical perspective, all those here who have maybe taken this type of algebra class, we would have, say, roster notation of 0, 1, 2, 3, 4, and 5, meaning we are only talking about those specific values. Whereas here, if we wrote it, say, as interval notation, we'd be talking about, say, a height from, say, 60 inches all the way up until, say, we'll say 72 inches, say somebody's 6 foot tall, okay? That includes every single number between 60 and 72. That's the difference between discrete and continuous. Continuous is every number in between. How many numbers are there here? 6. How many numbers are there here? Infinite. Because we're talking about 60.1. We're talking about 60.05. We're talking about 62.43. Get my idea? Every single number in existence. So again, this is a set of 6 numbers, and this is an infinite set of numbers. Okay? So today, we don't want to talk about the continuous random variable. We simply want to talk about the discrete random variable. Okay? So within this exercise, you're going to be looking at what we call like a probability table. This is a probability table right here. And it says, consider the following probability data table of the number of jobs a person has before the age of 40. Talk to the person next to you and say, how many different jobs do you think that your mom or dad has had in their lifetime so far? Just, I know you don't know their complete history, but how many different jobs do you think they've had? Go ahead, talk. What do you think you got?
Wait, combined against or separate?
No, each one.
I don't know what my mom did like.
Yeah.
I'm just kidding. It's not my dad is my dad is
Okay, so what we're going to do is we're going to make a histogram of this data, and we are going to go ahead and then describe that shape. And what we want to do is we want to take our values. People have either had 0 jobs, 1 job, 2 job, 3, 4, 5, or I wrote 6 plus because I didn't want to carry things on out forever. So I just went 6 plus at the end. And all of these probabilities here will always be between 0 and 1, okay? 1 represents 100% probability, 0 represents 0% probability. 0.15 represents 15%, okay? So if I make this, we'll call this, say, like a 0.2, a 0.4, 0.6, and 0.8. All I'm going to do is kind of make a bar graph or a histogram that describes this situation. So the number of people who have 0 jobs is 0.02. So just 2% of that population has 0 jobs. So I'm just going to go ahead and raise it up to 0.02. And the number of people who have 1 job would be 10% of people. The number of people who have 2 jobs would be 15% of people. Four jobs would be 38%. 5 jobs would be back down to just 8%. It says make the histogram and describe what you see. I would say it's fairly symmetrical. And bell-shaped. Again, in this class, we talked a lot of times about a normal distribution where things are bell-shaped. Okay? And as we see that bell-shaped curve, would you say this is more skewed to the right or more skewed to the left? Where does it trail off a little bit more? Does it trail off more to the left or more to the right? Yeah, it kind of trails to the left a little bit, right? I would write slight skew left. The next question says find P of x greater than or equal to 3. And what this means is the probability of x. X is the number of jobs. So what is the probability that an adult, by the time they're of age 40, has had 3 or more jobs? So the sum of that will tell me the probability that they have had 3 or more jobs by the time they're at 40. So 0.02 and 0.08 is 0.1. And 0.1 plus 0.3 is 0.48. 5868, I got 0.73. 0.73. What does that mean? That means 73% of people by the age of 40 have had 3 or more jobs. How does it make you feel that you are going to school to study for a career and that you might change that career? Does that bother you at all? Bothered me. I definitely wanted to choose a career, and that was the career I was on. I've switched jobs a couple times. I've been in this job for a while. This is my 18th year at Albert Lee. But I worked at a camp for about 6 years as well. I worked at a different school. I worked with my dad for a while, different things like that. Okay, so there's a real life scenario where you see that actual probability table. Okay, let's go to a chance situation as we see this play out a little bit more. It says, suppose you toss a fair coin 3 times and x represents the number of heads. Find the probability distribution of x. You're going to do this in your assignment, but instead of doing 3, you're going to do 4. Okay, all right? So I'll do one example for you. If I flip a coin 3 times, is it possible I could come out with heads, heads, and heads?
Yeah.
Yep. Give me another possible outcome.
Heads, tails, heads.
Heads, tails, heads. Give me another outcome.
Tail, heads, heads.
Tail, heads, heads. So right now, Hannah and Maggie have both put tails once. Let's do tails just once more. Where would it be?
Heads, heads, tails.
Yeah, heads, heads, tails. Everybody agree that that covers all of, heads, 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 and it covers all where we just have one of the tails? Let's now go to two tails. Give me an option with two tails. Tails, tails, heads. Tails, heads, tails.
Again, so I got a question.
Yeah.
Sorry, this is kind of long. In football, we've won nine. We've won 9-0 in coin tosses. What's the percent chance of that?
Just all heads.
We've won.
They're all heads.
We've won every coin toss.
So 4, 8, 16, 32, 64, 128, 256, 512. 1 out of 512, which is approximately 2 over 1,000 approximately. So we got 0.002. So 0.2% chance that happens. Yep. So I would say actually at that point, people would start to say, okay, you're falling out of the realm of what's really possible. We're starting to wonder if the refs are like giving you a break or something. So. Anyway, yep, so there's the probability there. Thank you. That wasn't too far off. That was a kind of nice interjection. What else we got? Two tails. What else we got?
Heads, tails, tails.
Heads, tails, tails. Thank you. And we have no tails, we have one tails, we have two tails, and the last one would be 3 tails. Excellent. Okay. So there we have it. Okay. We're going to make a probability table. And our probability table is going to be number of heads and probability. Okay. And our options for heads are we could have no heads, or we could have 1, 2, or 3. How many total possible outcomes are there? There are 8 possible outcomes, right? Okay. How many of those would give us 0 heads? 1. So the probability would be 1 out of 8, or 0.125. Okay? Always write as a decimal between 0 and 1. And if you have to divide that on your calculator, go ahead and divide on your calculator. I happen to know that 1/8 is 0.125. How many situations do you have just 1 head? 3. 3 out of 8 is 0.375. How many situations do you have 2 heads?
3.
3 as well. 3 out of 8 is 0.375. And how many situations do you have 3 heads? You have 1 situation, and there'll be 1/8 or 0.125. Okay? Talk to the person next to you. What do you think you get if you add up all of those? Go ahead. What do you think you get if you add up all those? Go. You should always get 1. That is the sum total of all possibilities. All possibilities must sum to 1. All these must be values between 0 and 1. We could draw a histogram and see this all play out. We have 0, 1, 2, and 3 options. As I make my histogram, I'm going to go 0.2, 0.4, and 0.6. I'm only going to go up to 0.6. Notice that my values only go up to 0.375, so I don't have to go too high. My first one would be 0.125. Next would be 0.375. 2 would be 0.375. What do you think? Bell-shaped? Yep. Is it symmetrical or is it skewed? It's very symmetrical. I want you to do letter C between you and a partner and see what you get. Go ahead, talk about letter C together. Go.
Two or more.
Oh, because
Oh, less than two?
Order and see.
oh,
Two or more. So it's.
oh wait, we're doing this one.
Or no, or Eight plus. Oh,
Wait, do you count to 5? So 50. Is government and Christmas?
Maybe I'm wrong, but I don't know.
so 87.
I guess I might be wrong. I'm probably wrong.
Probably, but. Two or less. Two or more.
The probability you have 2 or less heads is 87.5%. You simply add up all of those. Am I correct? Notice that it says equals, so you include the 2. If it didn't say the equals, you would not include the 2. Got it? Okay, good. You have a general understanding of the probability table. Let's go ahead and make use of it. And we eventually want to come to a game of chance and insurance. Kids and toys. In an experiment on behavior of young children, each subject is placed into an area with 5 toys. Past experiments have shown the probability distribution of the number of toys played with by a randomly selected group of subjects. Some kids like to take each of the 5 toys and play with each one of them. Some kids are more drawn to just playing with one. It looks like in this situation that some kids, actually 3 out of 100, didn't play with any of the toys. I don't know. Maybe they were sitting around doing some math and were just very intelligent. Looks like 30% of the group decided to play with 2 of them. It says, write the event plays with at most 2 toys in terms of X, and what is the probability of this event? So what that means is this, okay? The probability a child plays with at most 2 toys is probability a child plays with at most 2 toys is, go ahead, compute it, probability somebody plays with at most 2 toys. Five, four, three, two, one. At most 2 would be 0, 1, and 2, right? And so we would have 49%. Go ahead, see if you can answer 3. 3 says describe the event X is greater than 3 in words. And what is that probability? Make sure you describe it. What does X greater than 3 mean? Is that right? Probability a child played with more than 3 toys is 28%. What's different about calculating the probability x greater than or equal to 3? Yeah, you're going to include this, so I'm going to add the 23 onto that, and that's going to go ahead and bring me to 51%. All right? Suppose we grab a person aged 19 to 25. Well, you answer the question first. And we'll say if you're in a sport, it does count. How many days have you worked out or gone to the gym or gone to do like serious exercise like a sport in the past 7 days? Oh, the past 7 days, how many of those 7 days have you gotten in a really good workout? Go ahead, Tom. Where are you at?
Like 5.
I know when I was your age, it was very, very rare for me to have any day of the week in which I didn't go and get a really good workout. If there was a day, it was generally going to be a Sunday, but without a doubt, every day I worked out. Even when I got into college, just about every day I worked out. And I always said when I got to this age, I would still work out all the time. How many days do you think I worked out in the last week? None. How many days do you think in the last month I worked out? None. Last time I worked out would have probably been like doing something at a track practice. Like it's just falling apart. I need to get back at it, don't I, Gilly? Yeah. Sometimes it makes fun of my lack of shape and stuff. I get it.
I do.
Yeah. I hear you talking to Noah. You know, during calc, you guys talk about how weak I look and small. And, yeah. I get you. So you got yours coming. Okay, so this is at 68% of people didn't work out at all. 5% of people worked out 1 day, 7% 2 days, so on and so forth. The question is, show that this is a legitimate probability distribution. A legitimate probability distribution must be as follows. All probabilities are between 0 and 1. That's the first criteria. There's only 2 criteria that we have to meet. And notice that we have all these probabilities are between 0 and 1. Anybody know what the second criteria is? We already talked about it once. They all have to add up to 1. So let's make sure they do add up to 1. The 68 and the 2, that makes 70. 75, 82, 90, 95, 99, 100. We might end up with 0.99 or 101 depending on a rounding error, but we just added them up and they all add to 100. 100% or 1. Good. Let's make a histogram of this distribution.
Are you for real? What are we doing now? What is on the
The first one goes up to 0.68, but after that, look at how low all of them are. I got 5%, 7% is about the same, 8% isn't much better. Got another 5%, a 4%, a 1%, a 2%. How would you describe this?
People are lazy.
Okay, a lot of people are not working out, okay? We won't say lazy. Maybe they're taking care of children. Maybe they're going to their son's football game and cheering them on, right? all sorts of things. But at the end of the day, they're not getting in their workout, are they? Okay? Huge concern in our society is that we don't exercise enough. It's probably one of the biggest concerns that we have overall. But we would say this is skewed what? Skewed is the direction that it tails off, and it tails off to the right. So if it is normal at all, which it's tough to see that it would be normal, it's not symmetrical, it's very much skewed to the right. It says describe the event y less than 7 in words. Y less than 7 means the probability that what?
Oh, work out less than 7 days a week.
Someone worked out less than 7 days a week. I don't want to go through and add all those up. Like, that's a lot. Like, there's 6 numbers there. That would take me at least like 14 seconds, right? What is something else I could do instead of adding up all those numbers? Subtract what? Yeah, subtract the 0.202 off of 1, right? So, the probability that someone worked less than 7 days a week is 98%. And finally, this is where we're going to stop, just in my pacing. We're going to do expected value and mean tomorrow. So we'll do this last part here. Express the event worked out at least once. So the probability someone worked out at least once is, and how would I do that? Probably someone worked out at least once.
Minus 0.68.
Yeah, I know that it is at least once would be all of this stuff right here. And so I just have to subtract 0.68 off of 1, and I would get 32%. And I noticed I made one mistake. This is what they want you to do here, okay? Express the event worked out at least once in terms of y. This is what they actually want. What is the probability that y is, and how would that compare to 1? Less than 1, less than or equal to 1, greater than 1, greater than or equal to 1. Which one is it?
Greater than or equal to.
Greater than or equal to 1. That's what the book is looking for in that situation. I'm sorry I didn't put that for the other one, but when it says express it in terms of y, that's what it wants there. Okay. So your assignment will be for today and tomorrow. Today we get used to distribution tables, and then after that, tomorrow we get to gamble. Woo! Does anybody know somebody in here who is good at? No, let's see. Good at gambling. There's nobody here is good at gambling. Anybody know somebody here who has a gambling issue? There we go. Let's not embarrass anybody. Please use their initials so we don't actually use the names. Yes, tomorrow we will gamble. Okay, tomorrow we will gamble. Be ready. We're going to see who's going to win and who's going to lose. So bring your money.
Let's play Matter.
I'll go ahead and make it.
I forgot to use your last, but yeah.
Oh, yes, that's right.
Well, I guess what? It's spirit. Oh, yeah.
So we're just work out
You did?
at least once.
Yeah, what is that?
So at least once means one or more, right?
You guys get it.
Yeah. That makes sense? Sorry about that.
They can stomp. They can stomp. I gotta hand you guys what I did, right?
I forgot, I need to hand back your test.
So I literally was just rushing.
Spell it.
Also, when you get just do over.
If you are working on your homework right now, you'd be able to do problems 1, 2, and 3. You would not yet be able to do 5 and 6.
Yeah, near the top. Here, can you just, 18 and 17? And then.
Good. Let me know. I will start around with you. Only if Sam would go.
Here.
No way to start up that. That's unfair.
Every
I
time
hear
he scored a
one.
touchdown with the extra point, he started him and Saul.
I'm not putting in the box, just leave on board.
I think I probably sound
Jens, how are you doing the first one? Like, flip it forward.
So if you look at our first example, we put 1 3 times.
He goes, he perhaps.
I could not imagine.
There's a way to do that, but I don't think
Oh, Kenna, if you want to head out, we go over the test. Oh, you too.
It was not accurate. It wasn't the whole city. Just people who share their
Oh, you said it was
thoughts.
voluntary?
Yeah.
Shoot, I said experimental.
It's gonna take.
It's not voluntary when you're on, but
Yeah.
I just got the last one wrong.
I don't know.
Oh, I didn't randomize it.
Those were all kind of. Wait, no, I think there's one kid on top. There's someone on top. I know I do get some.
You do everything that
We hired one
This guy's a now here's a guy.
Oh, you're good. I think it's really the only one
I got this one.
I messed up the last one. Didn't write one. I mean, we both read Sam and Gallus on.
Okay, he's kicking your butt in calculus right now. Okay, so,
But just not count. Just not count.
So the first problem, I just want you to know, again, when it says that, they're receiving letters that people are just sending in, that's a voluntary response. When the city tries to get a sample by going and ask people at the library, they're doing it because that's convenient for them. So voluntary response, convenient sampling, important within that. I got your feedback on number 3. For next year, I'm going to add in a certain sample size that you're looking for. And make sure that that's worded properly. Other than that, the second page, problem 4 went very well for people. They understood that number 4 was an observational study. There was no treatment given. Number 5 was an experiment. It was interesting 5B. Is it reasonable for doctors to conclude from this data that the shoe reduces foot pain? I would say in general, yes. A couple of you guys said no. And you did give a good reason. And if I was, swayed by your reasoning, and some people said that there really wasn't, like people should have known that it should have been They shouldn't have known which shoe they were receiving, or there should have been some type of a placebo treatment involved, which I don't know what that looks like with a shoe, I guess. But I did give you credit for that with your reasoning. Lurking variable, they didn't control how much the people were walking around, did they? So they really should have said, hey, on a given week, this is what we want you to be walking. Give them some type of instrument to measure that. The most important thing for 11 and 12, a number of people did not say randomize your patients. So important to make sure as you break them up that they are randomly broken up into different groups. And obviously we do need to compare the results. I did allow for some different options for number 12, but overall you guys did a good job. This was a nice test. I do have these into the grade book. And remember, you get one retest per semester in case you'd like to see me at all. I'll take these back from you.
Oh, no. No, the scoreboard says.
Thank you. Good job, good job. Good job, good job. Thank you.
He knows it all. He knows it all.
Wow. Right? So you first want to break these up into types of values. So we first want to break up the full positive,
And yet it was right.
and then from there,
And yet it was right.
that's right.
So do not talk after.
Or is correct, but that is that something assigned we don't randomly assign them. We don't randomly assign to those spots. We pick those spots.
Sorry, that's my
We randomly assign them after that to the treatment.
Sorry, I'm the smartest in this world.
Wait, you did your study guide too, right?
Yeah.
No, I do not have the study guide in yet. I need to do that.
Oh. Yeah, I didn't.
Yep, exactly.
Everyone.
What are you talking about?
Takes
I was trying to.
probably first and only 100
Oh, yeah. I can't remember. I think 100%.
Yep, 16. Yep. 16 possibilities. Thank you.
I can't hear. I want.
No, it means you got 29, 30, and I'm just a nice teacher.
So on a dice one, it's it 36?
For rolling 2 dice, it's 36 possibilities.
Sweet.
Yep.